Well, it's time for part 3 of our gas laws, looking at, of course, Avogadros Law, which will deal with the amount of substance in mole of the gases that we're looking at. So Avogadros Law is the relationship between volume this time and the amount of substance in mole. So if we are looking at V and N, then we must be keeping everything else constant. So that means that our temperature must be constant and our pressure must be constant. So we're not going to change pressure, we're not going to change temperature. So I'll leave you this time to go and have a look at that simulation yourself if you want to have a look. In order to add extra amounts into the gas tube, we actually use the plunger here, and you can add different gases there if you want as well. But essentially what you should find is as you add gas into here, our volume will increase. If we release gas using this valve here, our volume will decrease. So what does that mean? That means mathematically, if we go to describe Avogadros law in the same way we have for Boyle's and Charles, we will discover that equal volumes of gases at the same temperature and pressure contain equal numbers of particles, because our volume is directly proportional to the amount of gas that we have there. This will become particularly relevant to us when we talk about a quantity called molar volume. But essentially what it means that if I have half a mole of helium, it will take up a smaller volume than if I have 2 mole of helium. If I had 2 mole of helium, it will actually take up exactly the same amount of volume as 2 mole of chlorine or even 2 mole of ammonia. So the same amount of gas at the same temperature and pressure will always inhabit the same volume. When we look at that relationship, it is again a directly proportional relationship. So our volume is proportional to the amount of mole that we have. So that means we get the same setup as what we did for Charles. V1 over N1 this time is going to be equal to V2 over N2. That's pretty much, we've had a practice it's using these kinds of calculations, so let's jump straight into some questions. This time we have 0.1 mole of sample of oxygen is occupying 2 decimeters cubed. So this is our volume. It's going to be our V1. This one is our N1. Sorry. And then we are asked to figure out what the volume would be if 0.25 mole N2 of oxygen had been placed into it. So what we're doing is we're adding an additional 0.15 mole and we're looking for V2 as our unknown. So if we have V1 over N1 equaling V2 over N2, we're going to substitute in. No need to change any units in this case. So we're going to have 2 divided by 0.1 is going to be equal to x, which is what we're looking for, over 0.25. So if we do this calculation, we will get 20 multiplied by 0.25 is 5. So V2 is going to equal 5. Check our units. It was decimeters cubed, so this will be decimeters cubed as well. And that makes sense. We've taken it to 2.5 times. So if we take 2 and multiplied by 2.5, we will actually get 5. So we can see that that relationship is indeed directly proportional, and that answer makes sense. Going on to question 2, again we've got our balloon situation. This time we have 0.35 mole of helium and it has a volume of 5 decimeters cubed at a certain temperature and pressure. This is just telling me that T and P are constant, so I'm okay to go ahead and use my V1 over N1 is equal to V2 over N2 equation. And I'm told a further 0.12 mole of helium is added. So I've started at an amount of 0.35 mole, okay, but my N2 is going to be 0.35 plus an additional 0.12. So it's actually going to be 0.47 mole that is actually in my balloon. Okay, so now I need to calculate the volume of the balloon. I have 5 divided by 0.35 is equal to V2 over 0.47. If I work this out, multiplying both sides by 0.47, 5 divided by 0.35, multiplied by 0.47, and we are going to get 6.71, and my units again, decimeters cubed. So again, my amount of mole has increased, so therefore so has my volume, and the answer makes sense based on those assumptions that we know about our system. Again, exactly the same process as using for all the other equations we've seen in the previous gas laws equations for both Boyle and Charles. Which means that we get to combine them all together, okay? So if the way we define a gas is always considered based on our temperature, our number of mole, our volume, and our pressure, and as we've seen, they're all interrelated into the way that they affect one another, we can actually bring the gas laws together. Okay, so we can combine all these relationships to come up with an overall expression for how the gas will behave. Okay, so the combined gas equation looks at the ratios of volume, pressure, mole of gas, and temperature. Again, our temperature must always be in Kelvin. Anytime we do questions with gases, our temperature must be in Kelvin. And when we have both and we have to have initial and final conditions, we can't use these relationships to calculate an instant in time. We'll use our ideal gas equation for that when we get there eventually. But this combined gas law we can use if we have an initial and final set of conditions, so where we're watching how the gas changes in its behavior. So the way we derive the ideal gas equation is essentially by remembering that Boyle's law is the relationship we get this pressure times volume is equal to a constant. Charles's law says that the volume divided by the temperature is equal to a constant. So now we've got this PV equals a constant multiplied by N and or T, N and T, or V is equal to this constant times N T over P. Avogadros law links volume and the amount of mole. If we don't worry about how we derive that, but essentially we trust that the maths work, what we get is this overall gas equation. Okay, where we've combined all the equations that we saw before into one equation, where we have P1V1 over N1T1 is equal to P2V2 over N2T2. If you think about this, what we can do is, if we know what's constant, we can remove it from the equation. So if N and T is constant, we can remove those from the equation, and we get left with Boyle's law, which makes sense because it was the relationship between pressure and volume where the amount of mole and temperature were constant. If we have a different situation, and this time we are having a constant volume and a constant amount of mole, we then get P1T1 over P2T2, which is Gay-Lussac's law. So anytime that something is constant, if a value is constant, it can be removed from the equation. So we don't actually have to remember all the laws. All we need to remember is which law equates to what. So Boyle's is the relationship between pressure and volume. Charles is the relationship between temperature and volume, and Avogadro's is the relationship between number of mole and volume. As long as we remember those relationships for our definitions, we can just remember the combined gas equation and just remove any terms that our question states as being constant. So it becomes a very useful equation because we can actually remember all three gas laws by combining this one gas law together. Okay, so again, this is just looking at the number of mole constant. If we keep the number of mole constant, so if we're dealing with a syringe or a balloon, our equation just simply simplifies down to P1V1 over T1 equals P2V2 over T2. And my pen has stopped working. Okay, P2V2 over T2 is all this one is, and this is just for n being constant. So as you can see, because it's constant, we can remove it from the equation. Let's have a look at a question. Okay, so this is a combined gas law equation. We're putting it all together. So we need to identify all our variables quite carefully. We have a 0.25 mole sample of gas. So this is going to be N1 in a 10 decimeter cube cylinder. So we have a V1 and it has a pressure of 100 kilopascals. This is P1. At the moment, I don't need to make any conversions. I have a temperature of 208 degrees C, which I'm going to add 273.152 to get to Kelvin. Second cylinder, so I have V2, contains gas at 100, so again I'm going to add 273.15 before I substitute it into my equation, and that's going to be T2, and then a pressure of 120 kilopascals. Check my units, they match, so this can just go into P2. So it's a sample of gas in a syringe. It hasn't said anything about adding or removing gas, so I can assume that N is constant. So I get P1V1 over T1 is equal to P2V2 over T2, remembering to convert to Kelvin. So I get, yes, oh, I'm actually solving for N. Sorry about that. It's actually asked us what is the amount of gas in the second container. So that means we have everything else. Always pays to double check reading your question. Let's substitute in. So P1 is 100. V1 is 10 all over T1, which is my initial one here. So it's 208 plus 273.15, which is going to be 481.15, and this is going to be multiplied by N1, which is 0.25. Remembering, if it's on the bottom on our denominator, we need to keep it in brackets. And then this is going to be equal to P2, which is 120 kilopascals, multiplied by V2, which was 15 decimeters cubed, all over 373.15 multiplied by N2. So if we get all this into our calculator, okay, divided by 481.15 times 0.25, so we're going to get 8.313 is equal to 120 times 15. So 1800 over 373.15. I won't take you through all the calculations, so we should end up with N2 being equal to 0.58 mole. Okay, so even though there's a large number of numbers in this, as long as we identify our variables clearly, we can substitute into this equation. And as you can see here, we were actually just looking for one variable, but we were given all the others in the equation. It's a simple substitute and solve. So that is it. We have done all of the initial gas laws that we investigated in class. And next up, we'll be looking at how this fits into what we call the ideal gas equation and putting it all together and coming back and talking about our real versus ideal gases. Good luck with getting through those, and thank you very much for sticking through with it. I'll see you in class.